that's all I wanted to say about last week's lecture. Now we come to a new topic. So the next 3 lectures will be the last story arc of the course before we do a wrap-up class next Thursday. There's also no new exercise sheet, by the way. We're done. We're just now running through the tail end of the exercises. You're going to get yours back this week, and then there'll be a final tutorial next week. What I want to do today is the beginning of a storyline that will go through 3 lectures, which starts with a bit of a story, a history lesson, if you like, that goes back to roughly 100 years ago. And I'll tell you more about why I want to tell you this story, but maybe as a initial motivation so you understand why I'm going off on this tangent. So first of all, we're getting towards the end of term, so maybe it's okay to tell a few stories every now and then. This is a bit like in school, the last week, you just watch videos. But also, I want to give you a bit of this historical perspective for 2 reasons. One is that in this field, machine learning, AI, and modern computer science that you're all studying or interested in, it can currently sometimes, I don't know about you, but for me it sometimes feels like we're very much sort of off the moment. We're thinking in terms of contemporary developments. And it can feel like things are moving so fast that we're detaching from all the stuff that has happened in the past. So I want to highlight with this story that some of the ideas that we're exploring today go back through the decades, even to a century ago, and actually have a much longer history than the way we think about them today. And realizing this connection may actually help us understand the dynamics of the field a little bit better. And the other reason is that I think some of the history of how and where these ideas emerged and the personal lives of these people, well, they help memorize stuff, but they also, I don't know, I find them sometimes soothingly general and long-lasting and sort of teachable. I'm not sure I'm going to get that across, but maybe over the next lecture, this one, then the one on Thursday, and you might see a little bit what I mean with this. So the story starts with this map, which is the place that we tend to call Eastern Europe in Germany. So the story I want to talk about takes place here. Does someone know what this town is called, this city? It's in modern-day Ukraine. Yes? Lwów. And it used to be called, well, it had many different names. For a while it was called Lwów in Polish, or Lemberg in German. It is, as you can see, it's in a part of Europe that shifted its, I don't know what the right word is, ownership, allegiance many times over the centuries. At the time when the story starts, in the early 20th century, it was part of the Austro-Hungarian Empire and was called Lemberg. But there was a very international community living there. People were speaking all sorts of languages, Polish, Ukrainian, German, and other languages. There was a very large Jewish population, and there was a very strong math department at the local university, which is the oldest university in modern-day Ukraine. And this math community there's a cool story that is actually quite well known in Ukraine and in Poland today, namely that there was a group of mathematicians there that would meet regularly in this place, which is a modern-day picture. So this is actually what it looks like today. It's a picture from Google Street View. Well, actually, the picture is from a few years ago, but it roughly looks like this today as well. This is a cafe in the center of town, which was called the Scottish Cafe back then, and it's actually still called the Scottish Cafe today. And here, so the cafe is here on the ground floor. The modern-day building on the top is a hotel now, and in here is the cafe. And in there, the local mathematicians would meet. This is a picture of the local mathematicians community. It's the Lwów School of Mathematicians. And first of all, maybe you'll notice that it's quite gender diverse mix. There's a lot of women and men in this picture. I've cut off the names of some of these people below because it wouldn't fit on the slide otherwise, but I can mention a few people. Here in the front and center at number 2, where's the pointer here, is Stefan Banach, whose name at least you've heard. Number 5 over here on the right is Stefan Kaczmarz, who you may not have heard about so much, but if you've taken a numerical analysis class or stochastic and numerical methods, you might have heard about the Kaczmarz method. Another person of note in this picture is in number 10, Stanislav Ulam, who we'll hear about more later, and also, is he in this picture? Yeah, number 4, where is he? Kuratowski, who someone with a math background might have heard about. So they would meet in this cafe. This is what it looks like today on the inside. Back then, it actually had marble tabletops. So they were tables that were covered with a marble slab, and they would write with pencil on those marble countertops, because you could wipe it out afterwards, and talk about math all night and drink. It was apparently actually more like a seedy cafe. These days it's quite, upscale, but apparently it was more like, just a place, like a bar you would go to. And then after a while, Stefan Banach's wife got annoyed with them writing on the table. She found that wasn't really particularly the right thing to do. So she provided them with a notebook. She bought a notebook that they would keep in the cafe, or one of them would bring it all the time, and then they would write questions in there. And it was called the Scottish book, because it was in the Scottish cafe. And there were people visiting from all over Europe. Mathematicians would come by on academic visits and give talks, and like they do today here as well, they would come and give academic talks, and they would meet in the evening in the cafe, and they would talk about problems and write them down. And this was sort of apparently a relatively new thing, to have this book, to write down a book of problems. And then there were prizes associated with particularly hard problems. When someone would solve one of them, they would give them a prize of sometimes even things that were back then quite expensive, like a bottle of brandy or so, or a live goose for one of the problems. This became, by the way, a bit of a tradition in math. Many math institutions today have a book like this. If you go to Oberwolfach, for example, the Mathematical Research Institute there also has a book of problems lying around in a corner somewhere. And if you get bored in the evening, you can open up a book and think about some cool problems. Here you can see 2 problems from Mr. Schauder, who was also on the previous picture. And over here is a problem by Hugo Steinhaus. And here's a problem by John von Neumann from 1937. He came by to visit, I guess from Hungary or from Vienna, to write down something. And you can see, if you read through this, that some of these are in Polish, some of them are in German, for example, over here, and in other languages. And one of the very prominent people in this community was this guy, Hugo Steinhaus. He was a mathematician born in, well, I can't pronounce it, Jászló, in the Austro-Hungarian Empire. He was born to Jewish parents, even though he himself was probably an atheist. And he was born into the Polish community in Austro-Hungary. So back then, Europe was even more complicated than it is now, maybe. And there was ethnic minorities in different parts of Europe that spoke even different languages. And he was very active in this sort of Polish community. He did his PhD in Göttingen with David Hilbert in 1911. There's a picture that you could find on Wikipedia of the Polish student math group in Göttingen. All the Polish students who came to Göttingen to study math. There's 10 of them, and he's standing on the right. And then he moved to this town, Lwów, Lemberg, where he became a prominent academic teacher, a professor of math. And he also raised an entire generation of PhD students, among them Stefan Banach and Mark Katz, Stanislav Ulam, others. Apparently, he met Banach in a park in Lwów, heard him talk about Lebesgue integrals. Lebesgue integrals back then were a huge new topic, and he sort of who's this guy? And got into talking with him, introduced him into this circle in the Scottish cafe. And he was actually the person who took this book, this Scottish book, with him when times got tough and kept it for posterity. So, because you can already guess, that was a difficult time, and things got very tricky for this town soon enough. In 1939, I think, after the Stalin-Ribbentrop Pact, the Soviets overran this part of Eastern Europe, and it became part of the Soviet Union. Actually, Steinhaus back then stayed at the university, but it was more and more difficult for him to teach. He writes later in his memoirs that he developed a physical disgust for all things Soviet politics and political management of his university. And then even worse, in 1941, the Germans in Operation Barbarossa came the other way and drove the Russians out and overtook Lwów. And there was a second massacre. So there was already a massacre when the Russians arrived, and then there was a massacre again when the Germans arrived. And a lot of people, I'll tell you more about this in a second, well, basically died. But before that, a lot of people went into hiding, and Steinhaus as well. He actually sort of went into the Polish underground, took on the name of a dead forest ranger. So the Polish underground furnished him with some fake passport of someone who just recently died. And he lived in a small town close to Krakow and pretended to be a forest ranger for a while. But he secretly kept teaching math. So when the Germans took over Poland, they made it illegal to teach in Polish or teach academic subjects in Polish. And so there were secret teaching places where the ideas of math survived. And Steinhaus was one of them. He taught in small places somewhere in the countryside. And because he didn't have access to books, he would write down the math that he remembered from his earlier days from memory, just on pieces of paper, and keep it alive that way. There's also a story. So he was an early, by the way, statistician, probability theorist. He wrote an early version of probability theory before Kolmogorov. He defined independence, maybe as the first person properly, and he did all sorts of fun stats pictures. So there's one of the problems in the Scottish book was like this. You have a mathematician, supposedly Banach, because he was a smoker, who has 2 boxes of matches in his trouser pants. And initially, they're both full, and they contain n matches. And now every time the mathematician wants to light a smoke, he just randomly picks one of his pockets, takes out a match, lights the smoke, throws the match away. By the time, and it's just uniformly at random, picks one of the pockets. So eventually there comes a point when one of the pockets is empty. He finds that the matchbox is empty. How many matches are left in the other pocket? I'm not going to tell you. You can look it up. If you get bored during this lecture, you can think about this problem. Here, another thing he did was, while in hiding, he tried to estimate the German losses on the front by reading German newspaper clippings and reading the obituaries of people who had fallen on the front. And he was looking for sentences that contained information about how many sons from that family had already died. So sometimes in an obituary, people would write, it's the 2nd son to die on the front, or the 3rd son to die on the front. And he was trying to do Bayesian inference, we would say today, to figure out, based on the frequency of how often a 2nd or 3rd son had died, how many people in total, what percentage of the population had been killed. You can also think for yourself about how you would do that. Nice, fun Bayesian inference problem. When the war ended, he sort of came out of hiding and moved to where large parts of the University of Lwów had moved to, namely to Wrocław in now Poland, where that university still exists. And he rebuilt the math department there, and it became one of the most prominent math departments in Poland. And he is often considered one of the fathers of the quite strong math community, education community in Poland to this day. One of the algorithms that Steinhaus came up with that I want to tell you about today is this one, which you may have heard about. Who's heard of k-means? Everyone has seen k-means. Nice. So he wrote this paper. By the way, so Steinhaus was fluent in pretty much every European language: French, Latin, German, English, Russian. And so here's a paper he wrote in French. That's the original paper. And it's just a 4-page thing, so I can recommend reading it for you, or I recommend that you read it. And his motivation for this, I think, is really cool because it shows how how fundamental these questions were that he was interested in. We tend to think of k-means as this tiny little algorithm that, that does a little bit of clustering. Today we say, clustering, this is like the unsupervised machine learning problem. But it's really a very deep question, namely, what makes a thing? The world somehow feels like it's continuous, but we think of it in terms of objects. We somehow mentally discretize the world into seats and rows and people and objects lying around. How do we do that? What makes a thing? We have this here in this final sentence. Diverse questions, even from anthropology or other practical fields like that industrial, right? That require the determination of fictive representatives of a population, right? So to separate a population or a set of points into subsets, such that within each object, things are most similar to each other, and they are most dissimilar from each other across objects. This kind of idea, this like similarity within cluster, dissimilarity between clusters, is also one that other people across the world, like Fisher, for example, for his discriminant analysis, also used. And so here is the algorithm, just to remind you. So it's an algorithm that takes two alternating steps. And it does that to assign k mean representers, k centers, to a set of points that are thought to like represent one joint body together. Actually, by the way, so Steinhaus, I think this is very interesting to keep in mind. In his paper, he actually, it's below here. The problem that this node is interested in is the division of one body, like one physical object, into n parts called ki to n, and the choice of these endpoints such that the similarity within cluster is minimized, or dissimilarity is minimized. So he's thinking of a physical object that has point masses that make up the object. And we think of these points as xi, now we would say data points. And we would like to cluster those points into representers that we call mk, the means. We call them means because we actually set them to be the means of the elements within each cluster. And to do that, we iterate between two steps. In the first step, we take those k-means and we assign every individual point to one of the means, namely the mean that is closest to it. And then we keep the means fixed. The other way around. And then we update the means, right? So once we know which element belongs to which cluster, it's easy to say where the center of the cluster is. And once we know where the center of the clusters are, it's easy to say which element belongs to which cluster. And that actually is the entire key idea that we'll talk about today and also the first half of the lecture on Thursday. So here's the algorithm again, now in a modern formal language. In Jax. It's a function. On the right, I have a little toy data set. It's the one that people always use to showcase k-means. It's this old faithful data set from this geyser in Yellowstone National Park in the US. So there's this massive old geyser, big hole in the ground that produces a huge eruption every hour, roughly. And so sometimes you don't have to wait for that long, but when you don't have to wait for long, then the individual eruption is quite short, something like 2 minutes. And if it takes longer, then there'll be more water coming out, and it takes about 5 minutes. I've been there once. It's a nice place. So it's really like impressive, like spectacle of nature. And so clearly you can see that there are these kind of two modes of this distribution, two clusters, if you like, and we'd like to distribute them into sort of representers. So what we do is we initialize at random the means. An efficient way to do that is to just randomly pick a point or k points from the data set. And then there's this while loop that iterates between, so this is just bookkeeping. Then we compute the square distances between the means and the elements, and then assign each element to the mean that is closest to it, and then update the means to be at the center, so the empirical mean, of all of the elements that are assigned to it. And now if I run this, you can see that this algorithm updates for a few steps, and then it terminates because nothing changes anymore, and now we have 2 clusters. A key point here is, by the way, that this is a while loop, and you can see that I did not have, I actually asked an LLM to write this thing for me, and it always really wanted to put there a maximum number of iterations parameter, something like, right, max iterations 100 or so, and you don't need to. This seems really dangerous, right? A while true loop. How can we be sure that it'll always terminate? It might be that I'm creating an endless loop here, right? This thing might never be true. So we need to think about whether this will actually always converge or not. It turns out this algorithm always converges for a very interesting reason. And so it's okay to write it like this. It'll just stabilize and then stop updating. So before I tell you more about this algorithm, though, let me finish the part of the story that takes place in Lwów. So I already said it came under occupation by the Russians in 1939, actually by the Soviets. Then for 2 years it stayed Russian. When the Germans arrived in 1941, there is a very sad part of that story is that the Germans, when they arrived, did what they called an außerordentliche Befriedungsaktion, which was a code word for killing off the intelligentsia of a town. So they found 25 professors and important sort of people from the city and killed them along with their family and servants in an attempt to quell any resistance within the town. Because the idea was that if you kill off the leadership of the town, then the normal people will just become a bit more quiet. Interesting perspective. By the way, in that sort of operation, they largely killed actually professors of medicine from the local clinic. I'm not sure whether this would play out the same way today, but in 1941, they thought of the medical doctors as the leading intellectuals. They didn't care so much about the mathematicians. So those mathematicians who were still in town, actually, they just sort of went into hiding largely. But it's still interesting to look at the lives of some of these people that were sort of in this Scottish cafe working on this book. Here's just a few that I picked from Wikipedia. Actually, since the last time I gave this lecture, the websites have been updated a lot. There's a lot more story now about these people. It's really good. I recommend you read up a little bit. One interesting person, and he's I pretty much picked them at random. Like the diversity of these life stories, I find somehow strangely interesting and soothing. Stanislav Ulam, I could have even given a lecture about when we did Markov chain Monte Carlo. Okay, so Stanislav Ulam he actually emigrated in 1939 to the US, where he got to work with people in the theoretical physics community. He made major contributions also to Monte Carlo methods. And he's well known as one of the fathers of the hydrogen bomb, together with Edward Teller. Teller, by the way, also an immigrant from Europe, right, a Hungarian, for the so-called Teller-Ulam design of H-bombs, which is the standard way to build hydrogen bombs, even to this day. And this design was actually found with Monte Carlo methods, with an analog computer that they would move around on a piece of paper to optimize the geometry of a nuclear bomb so that it would concentrate particles within the center that needed to start a chain reaction. So that's someone who got away and then made major contributions, maybe of questionable nature later on. Julius Schauder, who was also on the picture before, was not so lucky. He had a Jewish background. The moment the Germans arrived, he was imprisoned. He wrote a letter from prison to various mathematicians across the German-speaking part of Europe, also among others, so he wrote, for example, to Swiss mathematicians to ask for pieces of paper to write down theorems on because he was running out of paper. He also wrote to Ludwig Bieberbach, who was a German mathematician in Darmstadt, a student of Felix Klein. And that guy was one of the prominent members of the German mathematicians. He was like, he thought that Jewish math was somehow entarted. And he immediately denunciated Schauder when he received a letter to the Gestapo, and as a result, he was executed in 1943. So clearly not everyone back then was on the right side of history. Stanislav Sachs was, I think was also on the picture. He joined the underground in Poland and was arrested in Warsaw in 1942 and then executed as well. Kuratowski actually somehow managed to get to Warsaw and then teach there. He apparently survived the war relatively unscathed and established the Polish Institute of Mathematics afterwards. Mark Kach left several times. He had a scholarship in the US to study. He came back and forth before 1939 several times. In 1939, he then, when the war started, stayed in the US, and his entire family was killed in, it's a bit unclear how exactly, maybe in the Holocaust, maybe in some other form of mass executions, and he had to just be in the US and hear about it and live on with that. Nevertheless, Kach became a very, surprisingly, he seems to have kept his humor even through all of this. He's a very well-known math educator. He also wrote the biography of Steinhaus later on and various other people, and contributed to quantum field theory. Maybe you've heard of the Feynman-Kach theorem. Kaczmarz died very, very soon. It's a bit unclear how, probably as a Polish soldier in a German attack, maybe also in a massacre by the Russians. And Banach is maybe the most interesting story. He actually stayed in Lwów, and when the Germans arrived, because he also had a Jewish background, he had a hard time, basically, and he was actually saved by a guy called Rudolf Weigel, who was today we would say he was a biologist, who developed a typhus vaccine. Back then, that was done by extracting the human blood from lice that had been feeding on people, and the lice were transmitters of typhoid, and they had the antibodies. So he had to actually employ people as the feeders for these lice. Someone had to just sit there with like bags of lice around their legs and be bitten by them constantly so that they could afterwards be harvested. And he apparently employed a large number of Jewish scientists and helped them survive in this way. He actually was later, by Israel, named as one of the righteous among the nations for saving something like 500 people from the Holocaust by having them work as lice feeders in his lab. And actually, these people also then smuggled out some of the vaccines to the ghetto in Warsaw and so on. And one of them was Stefan Banach. So here is a leading, excellent mathematician reduced to be a lice feeder. But then so he actually survived the war, but in an irony of fate, he actually died of lung cancer in 1945, right after the war had ended. So this is where the story of Lwów ends for us. But we'll get back to some of these people the next lecture, basically, because they took some of the ideas, clearly many of which are connected to the ideas of statistics and Bayesian inference and machine learning that we are now studying today, to the US, largely where they went, and there they lived on. I'll tell you more about them later. So this k-means algorithm, to get into a thought of why this is an interesting algorithm and how it's connected to things we still do today, not just like this boring clustering algorithm, it actually converges for a very interesting reason. And to understand that, we can use a concept called the Lyapunov function. Who's heard of Lyapunov functions? Only one or two of you. So there's a concept. This is due to this guy, Alexander Lyapunov. He also actually has an interesting career. He was an educator, a math professor. Apparently he was quite a good teacher, and he didn't have much time to do research because he spent so much time on teaching. understandable problem. Mostly, the first thing one usually reads about him is that he was very handsome, as you can see in the picture, very good-looking guy. He was interested in dynamical systems. He was actually Russian, born in Russia, but then moved to teach at the University of Kharkiv, which is now present-day Ukraine. And he spent most of his time and most of his life in the place we now call Ukraine, and died in Odessa, actually, also in modern-day Ukraine. And his main contributions are to the theory of dynamical systems. And he provides this idea that says, if you are to analyze the dynamics of a dynamical system, just like k-means, by the way, which is a dynamic algorithm, right, which iterates across discrete steps, one can try to study its convergence by trying to find a function called the Lyapunov function, J, which is a positive function that depends on the algorithm state variables and can be shown to decrease in every step of the algorithm. If that's the case, then because it's a positive function, you can guarantee that the algorithm will eventually converge because it decreases that function in every step, and then eventually it can't decrease it any further, and then it has to have reached a stable state. And a typical interpretation of these functions is as a form of energy of the system that gets reduced in every step until we find the minimum of the energy. So for k-means, such a function can be defined as this J here. So here's the algorithm again. I've just rewritten it in a more pseudocode way. We initialize the means, and then we iterate between assigning these so-called responsibilities of each cluster to responsibilities of the means for the data points. So the responsibility goes from means to data points. And then updating the means by going through all the data, checking for their responsibilities. The responsibility in k-means are binary variables, so which datum belongs to which cluster, and then updating them. This is maybe like a weird way of writing this. This is supposed to be a sum over, so R are the responsibilities. You can think of an array of size k, number of means, by n, number of data points, with binary entries. And so this basically counts how many elements are in each cluster, and this tells us which element belongs to which cluster. And here, this is effectively a cluster-wise mean computation to update the mean. The Lyapunov function that we want to show gets decreased in every step is this function. So it's a sum over the number of data points and the number of clusters times the responsibility of each cluster k for datum I. These are binary variables. They're either 0 or 1. Times 1/2 times this L2 distance, the square distance between the datum and its cluster mean. So first, to show that this function actually decreases in every step. So clearly, this is a positive function, right? Because the r's are either 0 or 1, and this is a positive or non-negative number. And so this whole thing is a non-negative number, sum over non-negative numbers. It clearly decreases in every step of the algorithm because here we literally set r to the minimizer of this term in here. So, I mean, clearly this minimizes this function in step 4. And in step 5, we can also show that we are minimizing, so this line here, that we are minimizing the function by taking a gradient. So if you take a gradient of this expression with respect to the mean, then okay, so we don't need to set a minus here. Let's check. Okay, so so why is there a minus there? Let me check. Let's just see. I don't know, of course, there's a minus from the gradient. Sorry. Okay, so if you take the gradient of this with respect to m, right, the 2 comes down, cancels with the 1/2, and the chain rule tells us that the inner derivative is -1. Yeah, so that's where the minus comes from. Whew. Okay, that's good. So we want to set this to 0. We rearrange. To do that, we break up this sum into 2 parts, right? The sum over the xi and the sum over the rik mk, where the mk we can take outside of the sum because they don't depend on I, right? Rearrange, you get this expression for the mean, which is exactly what we set it to. So that's the update. And we can take the second derivative of this expression, which we find to be just a sum over the rik, because these are binary variables, either 0 or 1. This whole sum has to be larger than 0. So it's a positive curvature, convex problem. We're finding a minimum. So this energy function is the thing that k-means minimizes. So now let's try and move forward a bit towards probabilistic machine learning. In which sense can we think of this in a probabilistic fashion? So can someone guess what this function is? I've already said that it's an energy. What does the word energy usually imply? Yes? Yes. So energy is the negative logarithm of a probability distribution. And in this case, we can think of this as a probability distribution for the xi given the mk and the rik. So this is a likelihood. And so this is supposed to be a negative log likelihood of something. So what's the corresponding probability distribution? It's the exponential of minus this expression. So if you take the exponential of a sum, it turns into a product. And what we see here is that up to normalization, this is a product over both the data and xi, and the clusters k, where in each factor in this large product, we have something that's e to the minus 1/2 times square distance, so that's a Gaussian. Right? So it's a Gaussian for xi with mean given by the mean k, the mean from k-means. Good thing. With standard deviation 1, because right, that's just sort of the implied thing if you have an L2 norm, so standard uniform covariance, raised to a variable zik, which is a binary variable with the property that across k there's always 1 and exactly 1, and everything else is 0, so it's like a one hot thing that selects Gaussians from the k different choices that we could have. So here is a graphical model for this. You've already seen graphical models with variables and arrows. There's a little twist to this notation that is quite common for graphical models. I've drawn these rectangles, which are called plates in this nomenclature of graphical models, that they represent copies. So there are k clusters and n data points, and n times k of these indicator variables z that tell us which cluster each datum belongs to. So what we're doing here is we're finding a maximum likelihood assignment for the means of these k clusters by inventing latent variables z that tell us which cluster each datum belongs to. There's a question. So the question is, how can we be sure that we'll actually converge in finite time? Just the fact that we decrease the energy function in every step doesn't guarantee that we'll converge in finite time. The reason this converges in finite time is, at least in this case, is that these are discrete. So there can only be discrete steps changes, right? There is no possibility to have some kind of asymptotic convergence. And so at some point, as you can see actually in the algorithm, where is it? I'm checking for discrete changes in these assignments. And so there is no way to asymptotically decrease a binary variable, right? Eventually, there's just no more change. And then you're done. OK. So I'll take a break now. I just want to highlight, draw your attention to a key structure here. Namely that this algorithm works by creating a new variable, a latent variable, z, which tells us which datum belongs to which cluster. So that variable is actually not a part of our mixture model. Right? Our mixture model says for each datum, pick one of the clusters and then create an element from from the cluster by drawing from a Gaussian with the mean given by mk and a standard deviation 1. That's the generative process that's assumed in this likelihood, if you read it as a likelihood. And the algorithm becomes like tractable. It gets its nature from the presence of these latent variable Z, which we don't actually observe. So we invent them. And by the moment we invent them, suddenly the rest becomes easy. And that's the underlying structure here is that if you know what the clusters look like, then it's easy to tell which datum belongs to which cluster. And if you know which datum belongs to which cluster, then it's easy to say what the clusters look like. Because estimating the mean of a set of points is very cheap. And finding the nearest mean, the nearest cluster for each datum is also cheap. But jointly, the problem is much harder. So if I would have written down this likelihood without the Z's, then it suddenly becomes a much harder problem to optimize. And that structure, this simplification through the presence of a latent variable, is what we're going to look at after the break, because it's actually a very powerful idea that will lead us to an even more powerful idea. We'll reconvene in 5 minutes. Now okay, so I introduced this notion of, this is actually called, so the idea that we're trying to get to is called induced factorization. And so just maybe let me summarize again. I said there's this algorithm called k-means, and it assigns means. So, and how does it do that? Well, the only thing given to us are these data points x. That's the whole thing, right? So the black circle means something you can see, white is stuff you don't know. So remember that the data set I showed you, I mean, let me go back to it. Here's a picture. The data set only has these dots. That's it. That's the entire thing. That's just x. No one tells you what belongs to which class. But it turns out that by inventing this extra variable, this assignment variable, this is clearly something that is a human contribution. It's not part of a physical data set. We suddenly get an algorithmic structure that is intuitively very easy to set up. If I know what the clusters look like, if I know M, then Z is very easy to estimate. I just pick the nearest cluster center. And if I know what the sets are, so if I know which datum belongs to which cluster, it's very easy to estimate the means. It's literally just an empirical mean. Question? Oh, I forgot a minus here. Yeah, so this minus there should be a minus here as well. The thing inside the sun logarithm will be what? No, so if you take the exponential of this with a minus, then you take an exponential of minus something squared, which is a Gaussian. And yes, so if you like, then a Gaussian is 1 over something squared. But it's just, yeah, so it's e to the minus something squared. Okay, so, and this algorithm, then, so having this structure gives us this opportunity to do these iterative updates, Z, M, Z, M, Z, M, I mean, where the Zs are actually updated as these Rs, as these responsibilities. And that actually converges quite fast. I mean, I didn't really tell you theoretically that it converges fast, but you saw the updates. It's like 5-6 steps, it's done. So it turns out that that structure, this update, this iterative update, can be generalized in a very powerful notion. And this is where another person comes in with an interesting history. Here he is, Hermann Otto Hirschfeld by original name, but then he called himself H.O. Hartley, Hermann Otto Hartley. He was German by birth. Born in 1912 in Berlin. He studied in Berlin as well. He got a PhD from the University of Berlin at the age of 22 in math in 1934. So you can imagine that that was already an interesting time, especially for someone like him, because he was a Jew. And so he emigrated in 34 right away, first to Cambridge in the UK, where he met Lehman Pearson, eminent English statistician, and became a prominent or active member in the stats community. And then he emigrated further to the US, where he was first in Iowa for a while, and then later went to Texas A&M. And he was apparently a very likable, humorous person, very short by nature, used to introduce himself to lecturers by asking people, can you hear me? And can you see me? As he walked in. And he wrote like several nice contributions to statistics. One of them is this paper, which is called Maximum Likelihood Estimation from Incomplete Data. That's exactly the idea we're interested in. So he talks about, like, you know, simplify the uniform of this, like maximum likelihood computations in the presence of incomplete data. So the idea is here you have a data set X that becomes much easier to think about if only you would know about some structural variable Z, which you can't observe directly. And then we show that this actually turns out that there is a nice algorithmic structure that arises when you add the sort of complete data. So here is that this algorithm was later extended by Dempster and others into something called expectation maximization, EM. Who's heard of EM? Okay, so we'll do a quick recap of EM. I think roughly half of your hands went up, so we'll quickly go through that. Because it's a completely non-obvious algorithm, I also have to like memorize it every time it comes up, but it contains this very powerful idea that we'll now derive. So what's the connection to the stuff we've previously done? I said at the very first lecture, everything we do is going to be Bayesian inference. So we'll write down likelihoods and priors and compute posteriors. Ideally, we'd like to compute posteriors, but that's sometimes hard. So when you have parameters in your model, eventually you'll probably do something like maximum likelihood or maximum a posteriori estimation. So you'll write down some generative model for your data, given some parameters. Then maybe you'll write a logarithm in front to make it easier to compute. And you would like to find a maximum of this expression as a function of theta. So this is an optimization problem. However, in general, this marginal likelihood will contain some variables that you don't know, some Z. So that will be our incomplete data setting. For example, in the story I did about Gaussian processes, we had this latent function that describes the CO2 content across time in our example that we went through, which we had to integrate out. So for a Gaussian process model, you can integrate out in a closed form. But if you have a more general model, for example, if you have the features of a function in here, the weights of a neural network that enter some nonlinear feature function, some representation, then this integral will not be closed form in general. So what I said so far, what I proposed as a potential approximate solution is a very sledgehammer type approach, namely that we forget about this integral for a moment and we find the mode of this expression both in y and z, so we optimize for a point estimate in y and z. Then we somehow maybe do some, so that would be just a maximum complete likelihood estimation. But that's a very like coarse approximation. In particular, you could have some nasty cases where your point estimates for Z are completely ill-posed. You saw some in your homework for this week, right, with these point estimates for the error of each scientist. What we could then do is we could try to find a curvature estimate of this in Z at the estimate Z star, or most likely estimate for Z, and then try to like do some Laplace approximation that gives us a Gaussian approximation for the distribution in Z, which we can approximately integrate out. That's always possible. Well, it's nearly always possible as long as there is a non-zero curvature here and this is a continuous variable Z. But that's a very general framework, which is why I introduced it to you first. It's also a very coarse approximation, right? We're sort of imposing some Gaussian structure on this estimate for Z, and that might not be a good representation of the true posterior. Maybe the true posterior over Z isn't even defined on the reals, and then this is really not a very good approximation. So instead, here is a new idea that's at the basis of this EM algorithm, which says if we get lucky, sometimes, just sometimes, we might be able to, instead of computing this quantity, so that's the logarithm of an integral, we might be able to compute the integral over the logarithm of this distribution with respect to this posterior over Z when evaluated at a particular point theta star. So here we're not integrating out theta, we're fixing theta to get an posterior estimate for z, and then integrate out the log complete data likelihood. So this is called complete data because it contains y and z. And then this gives us a function of theta. So here this theta is fixed, but this theta is enters as an expression in this log complete data likelihood. And now we can try and estimate a new update, optimize an update for theta. That's the structure we're going to get. And I know that when the first time I write it down like this, it's complete abstract nonsense, so we'll have to look at a few examples several times to understand why this works. This is called the expectation maximization algorithm after Dempster's update to Hartley's paper. Why? Because it computes an expectation of the log complete data likelihood, and then it maximizes this expectation with respect to this theta. So here is a definition of this algorithm again. The EM algorithm, the expectation maximization algorithm. Consider a model that contains some parameters and some observed data and some invented latent variables that you have smartly chosen such that the distribution becomes easily tractable. And then do iterate between the following things. Compute an expected log likelihood of the complete data under the posterior for the latent variables, and then maximize that expression with respect to this theta. So you pick a posterior given the variables, marginalize, compute an expected, sorry, not marginalize, complete an expectation of the log likelihood as a function of theta at that point theta t, and then optimize with respect to theta. So there's three interesting things to keep in mind here. The first thing is this is an algorithm that supposedly maximizes the evidence, so the marginal likelihood for y given theta as a function of theta. We'll need to find why this is even true. So I need to tell you why this maximizes evidence, because it doesn't look like it's maximizing evidence. It's maximizing this thing, right, which is not the evidence. Secondly, whoops. Now I've clicked on a link. Secondly, we maybe need to remind ourselves that this is not a general algorithm that will always work. It relies on us getting lucky. So we need to find a z, a latent variable, that we need to invent, such that this thing is tractable and this integral becomes tractable. So we need to have the full posterior, and then we need to be able to compute the expectation of the log likelihood for the joint model under this posterior. That requires us to be able to compute posteriors for any particular given value of theta, and to compute under this posterior an expectation of the log likelihood. So that won't always work. And then a second step, which we'll do on Thursday, will be to think about what we do if this doesn't work, if we don't know how to get this general, this analytic posterior. And that will lead us to an idea called variational inference. So first, let's figure out why this works. So why does this thing maximize likelihood? Question.
I wanted to ask about how you went from the case saying that they cast the because of exact, and then you use the EM algorithm saying, and from what I understood, it's also important because of this latent variable.
So your question is basically, how is this connected to k-means? Yeah. So far, the connection is just there's a z here and there was a z in EM. We'll find in about 15 minutes that k-means is an instance of this algorithm. Right? So the structure was, we had this k-means algorithm. That was like old thing, somehow interesting, and it works because it has this latent variable z. Now I'm saying here's a new, larger class of algorithms called EM, which also utilizes some latent z that somehow makes computations tractable. And we'll find out, so first we'll now find out why EM actually maximizes evidence. That will basically already be the important step, because clearly this marginal log likelihood was also what EM was maximizing. That was this J function. And then we'll just have to show that the J from EM is actually exactly the J that we're maximizing in EM. Say again, how do we choose? How do we choose the right Z? Well, that's going to be the trick. Yeah. So actually, for today and for Thursday, the story will just be you'll have to be smart. And somehow you just have to have this right insight to get the right set. And I'm not saying that to like be smart or sound funny, but that's actually for a long time, that was the game. Someone had to sit down and draw graphical models and think about structure. I'll tell you more about that on Thursday, but like as a sort of a like idea, when I did my PhD, that was actually how machine learning research worked. Like I spent 2 hours in front of a whiteboard with my mentors drawing these graphical models, which back then were these super powerful tools, to come up with the right latent variables such that everything became tractable. We'll talk about how tedious that was on Thursday. And then we'll discover that today, with modern automatic differentiation and neural network structures, we can actually automate that process, give it more flexibility, apply it to larger classes of data sets, and that'll lead us on Tuesday to attention. Right? So that was the spoiler for the next few steps. So first, why does EM actually work? So I said this algorithm, which maximizes this expression, supposedly maximizes this expression, which look like they are different things, but they turn out to be related to each other. So what we did here is, and here's a way to think about what this algorithm does that is already like indicative of what's to come. What we did is that we constructed an approximate distribution for the latent variable z. I say approximate distribution in a very general sense, but actually we picked a very specific approximation. We said we're going to set this distribution to the posterior over the latent variable z when evaluated at our current guess for the latent parameters theta. So we call them theta hat. But we could have picked another distribution over z that somehow depends on theta. We just happened to choose the posterior that arises under this joint model. So for any such approximate distribution over z, assuming it has full support on the joint distribution, the following holds. So on the left, we have the thing that we want to maximize. That's our log likelihood without the latent variables. It's the marginal log likelihood, also known as the evidence for the model. By definition, that's this thing. It's the evidence. So now what I do is, assuming that Q has full support, I'm allowed to multiply by 1, right? By Q over Q. So that's an easy step. And now I use something called Jensen's inequality. Who's heard of Jensen's inequality? Enough people that I can just say, yeah, you know. So Jensen's inequality states, oh, something broke here? Ah, weird. So before the lecture, I wrote an extra sentence here. Maybe it's on your slides. It says, you can think of this as saying the expected value of, so the phi of the expected value of G under mu is less than or equal to the expected value of phi after G under mu. So basically, if you have as long as phi is a convex function, if you exchange the integral and the convex function, you'll get a lower bound. So the proof for this is basically like a version of like the midpoint theorem, roughly, right? Like in function space. Okay, so that means if you apply this inequality, then we get from here to there. So this is an upper bound for this. So what have we done here? We've taken the logarithm inside, and we're allowed to do that because the logarithm is a convex function, or actually it's a concave function, which is why the inequality is the other way around. Sorry, right? It's a concave function, and therefore the inequality goes the other way around. Here, like this. So now this is a lower bound on this. And now what we see here is that this is Q log P of x given z. So that's the quantity we are computing on the previous slide. Right? The expected value of the log complete data likelihood under our approximation Q, which happens to be the posterior. And then we get a minus Q theta hat z log Q theta hat z dz. That's an entropy. So an entropy is an expected value of a logarithm of a distribution. So that's why I write an entropy here. But the important thing is, and again this broke, I made an update to the slides that somehow didn't get updated here. This thing, remember the Q only depends on theta hat. So as a function of theta, this doesn't depend on theta, right? It's just a constant, just a number. So we can give this a new name with a curly L. That's sort of indicative of something big and important. And the important thing is that as a function of theta, we can think of this as a lower bound on the evidence that we are trying to maximize. So that means that when we maximize this function as a function of theta, then we are increasing a lower bound on the evidence. That's why this is called an evidence lower bound, an ELBO. Who's heard of the ELBO before? Half the room. Good. So this is where our ELBO comes in. Every time the ELBO shows up, you have to remember, what is this complicated ELBO thing again? So for those of you who raised your hands, you're probably currently doing this. It's this thing, this expression. And what we're doing in this algorithm, in this EM algorithm, is to iterate between updating this estimate Q to set it to a new posterior given a new value of theta, and then maximizing this ELBO as a function of theta. So this almost sounds like a good algorithm, right? So there's this thing that we want to maximize. It's called the evidence. We found a lower bound to it, and now we increase the lower bound in every step. Well, that's great, but it doesn't guarantee that we'll actually increase the evidence, right? Because we might have a gap between our lower bound and the evidence, and we just keep increasing the lower bound, and the evidence never grows. So what we now need to show in a second step is that our particular update, our choice to set the estimate to this, actually happens to make the bound tight. And then when we increase it, we also increase the evidence. And then as we increase the evidence, the bound will become loose again. Then we update again to make it tight. We increase again, the bound becomes loose again. We update, and so on. So to show that, I need to introduce one more concept, which is an expression for the gap between this ELBO, the evidence lower bound, and the actual evidence. And that gap happens to be called the Kullback-Leibler divergence between Q and the posterior over Z. So here are these two guys, Richard Leibler, Solomon Kullback. Yet more stories from the Second World War. So Solomon Kullback was also born to Jewish parents. He's from modern-day Lithuania originally, moved to the US very early, before the Second World War. Leibler was American by birth. Kullback was actually, I think, like the boss, basically, of these two. He became the third employee of an early version of the Signal Intelligence Service in the US, which later became known as the NSA, still exists to this day. He was the chief scientist of the NSA for large parts of his career, which means that he basically didn't publish anything. He published like one paper that people know about, for which I also, before there was a break somehow in my update here, had a link. Something really weird happened between me coming into the lecture hall and you arriving. Something broke. Do you have it on your slides? Huh, okay. Well, at least you have a good version. In which they introduced this object called the KL divergence. And we'll just construct it here. So here is our ELBO again, right? Which I copied over from the previous slide. It's this expression. So now what we'll do is we'll first use the product rule. So we write this joint as prior times likelihood, if you like, or as marginal times conditional. And then we rearrange. So we expand into this part, plus, because using the logarithm of a product is the sum of the logarithms, plus something that's p of x given theta, so it doesn't depend on z. We can take it outside of the integral, times an integral over what's left, which is q of z. So that's a probability distribution. So when we integrate over it, it's just 1. So now we know that the ELBO is actually equal to the thing we're trying to maximize, the marginal evidence, minus this thing. And this thing is called the KL divergence, Kullback-Leibler divergence, between this distribution, between Q and P. So the Kullback-Leibler divergence is not symmetric. There's a difference between the divergence from Q to P and from P to Q. This one is the divergence from Q to P of Z given x and theta, so our posterior. This is a divergence, so it's something almost like a distance. but an asymmetric distance, so it's not conserved under exchange of q and p, but it is always larger or equal than 0 and becomes 0 if and only if q is equal to p. You can show this for yourself. It's another one of these inequalities that you can sort of use to show this, called Gibbs inequality, if you want to try this for yourself. But it's just larger or equal than 0, and it becomes 0 exactly if q is equal to p. So what does that mean? That means in EM, in our algorithm, what we do is we write the marginal log likelihood, the thing that we would like to maximize, as the ELBO, this lower bound expression, plus a KL divergence between q and p. And then, so here's the definitions for these two things again. And so what we now have is we say that the log likelihood actually is lower bounded by the ELBO, as the name suggests, the evidence lower bound. And the gap from the ELBO to the marginal likelihood is actually the KL divergence to the posterior. So what the EM algorithm does is it iterates between first making the bound tight by setting the approximation q to the true posterior over z at theta hat. And then it maximizes the ELBO as a function of theta. As part of that step, a gap opens up between what is now the posterior over theta at the posterior over z at the new value of theta and our current approximation for the posterior at the old value of theta. And then the E step closes that gap again. Does that make sense? So another picture to draw would be that there's this sort of in theta space, there is this, right? So this space is theta. This here is the log of p of x given theta. And what this algorithm does is it's moving around in theta space. This is our current theta hat. Locally, we approximate this function with this expression, the evidence lower bound, something like this. So that's our ELBO of theta, comma q. And then we move to the new mode. And at this new point, theta plus, there is a gap again. And that gap is equal to the KL divergence between the old q and the new posterior. Now we iterate. So clearly, by doing this, we'll eventually converge to a local extremum of this evidence. That's it. So here is another way, here's this just summarized again, phrased together. The EM algorithm is an algorithm for finding a maximum likelihood estimate for a model that involves a latent variable. And the entire game is to find a good latent variable that makes everything work well. And it's finding a maximizer of the log evidence, which is this thing, in the following fashion. Oops. Still seems to work. It iterates between computing an approximation to the correct posterior over z by fixing a current estimate for the parameters theta hat and computing the posterior. When we do that, we can think about this as setting the KL divergence between our approximation to the posterior and the current posterior to 0, because that's how you set KL divergence to 0. You just make the left and the right-hand side the same. And then we maximize the evidence lower bound, which is a lower bound on the marginal likelihood where the gap of the lower bound is exactly the KL divergence. So as we move, the KL divergence will open up again. It will become a non-zero expression. We can then close it again and repeat. And because this raises a tight lower bound in each step, it's guaranteed to increase the evidence in each step it does. So now the final thing to do for today is to just show that the k-means algorithm is actually a special case of this. And we'll do that immediately by doing something slightly smarter, namely to learn the components of a mixture model, including the covariance. So I said so far that that k-means learns a Gaussian mixture where each Gaussian component has a standard covariance, where the covariance matrix is just a 1. So we're going to make things a little bit more interesting by also learning the covariance of this model. So here's this an expanded version of this picture that you saw before. This is our data that we get to observe. We now assume that this data is generated by drawing for each datum with a probability pi k, which is a discrete probability over the k clusters, a cluster membership for this datum, and then looking up for each cluster the parameters that make up the cluster. In our case, the cluster happens to be a Gaussian. We could pick something else, where we're going to, for now, pick a Gaussian. This is called the base measure of the cluster, of the mixture model. So Gaussians have 2 parameters, a mean and a covariance, and we'll need to figure out what those parameters are. So now let's translate this into the language of the EM algorithm. The EM algorithm says we need a model that has parameters. So our parameters, theta, are pi and mu and sigma k. Right? So for each cluster, there is a probability to be in the cluster, there's a mean of the cluster, and there's a covariance of the cluster. 3 of them, and these are actually, in general, this is a matrix. Right? And the log likelihood, marginal likelihood for x is this. Right? So the probability to be drawn is like the generative, it's actually down here. You can read off the full probability. Right? So the probability for datum xn is generatively, read from left to right, first generate a class identity, like which cluster are you in, draw from a discrete distribution with probability pi. Then, once you know which cluster you're in, read off the parameters of this cluster, so that's a Gaussian with this mean, this covariance, and draw an xn. And now our challenge is that as a function of pi and mu and sigma, this doesn't look like something we can optimize on a piece of paper. Right? If you don't have a computer, if you can't do gradient descent, I don't know how to maximize this on a piece of paper. So what we'll do is we'll invent a new variable called znk, which says, I know which cluster you belong to, and I'm encoding it in a one-hot fashion. So znk is an array of size n by k that contains binary variables, one-hot encodings, that tell us which element belongs to which cluster. Then the log likelihood has this form, and now we see, well, actually we don't see yet, but we can maybe get an inkling that this so-called complete data log likelihood might be something easy to compute an expected value over. Why? Well, because we're going to get a posterior over z. So z is a discrete variable. We'll get a discrete posterior. Discrete distributions are always easy to handle. Expected values of discrete distributions are literally just the value of the discrete distribution. And then we'll have to compute an expected value over the logarithm of these things. Well, but these things are exponential family distributions, right? So pi k is a discrete distribution. The logarithm of a discrete distribution is just a number, and this is a Gaussian, so the logarithm of a Gaussian will just be a quadratic form, and expected values of quadratic forms under discrete distributions might be easy to do. So let's see what EM tells us to do. So EM says, to maximize your marginal likelihood, consider the complete data log likelihood, which I've copied over from before, and now iterate between these 2 steps called E and M, expectation maximization. First, compute an approximation for the distribution over z that happens to be the posterior over z given x. If you do that, if you do this, then that means you are setting this KL divergence to 0. So let's see what this posterior is. Well, here we just use Bayes' theorem. So the probability for point n to be in cluster k is the probability for point n to be in cluster k a priori without knowing its exact value times the likelihood for the datum xn, so the probability for datum xn given which cluster it belongs to. This is where our induced factorization comes in. It's this, we've chosen a smart latent variable, so now therefore this probability will be easy to write down. The probability for z and k to be 1 is just pi k. That's our discrete distribution. And the probability to see xn, if it is in this cluster, is just a Gaussian. So we know what a Gaussian is. We just plug it in. And now we just have to use Bayes' theorem. So we need the evidence. We need to divide by the marginal probability for x. which is just the sum over all possible ways in which xn can arise. So it's a sum over the pi k times a Gaussian over xn with this particular mean and this particular covariance, and we sum over them. This thing is a number which we can evaluate, because if we have mu and sigma and pi, it's just a number, right? It's just a marginal probability. Sorry, not a marginal, just a probability. And we'll give it a name. We'll call it the responsibility of cluster K for datum n. Now, we need an expected value over this. So, well, the expected value under a discrete probability distribution is just the expected value. Well, it's just a value of the distribution at that point. So it's just R and K. And now we need to, in the second step, in the M step, maximize the evidence lower bound. So the evidence lower bound is actually this minus the entropy of this posterior, but that posterior depends not on theta, right? So it's at P of z given x at theta hat. Oh, here's the mistake again. There should be a hat here. Really, these slides completely broke. I'm not sure about this. So there should be, right? So if we would write down this curly L from before, it would be this minus an entropy that doesn't depend on theta. So if we maximize this with respect to theta, it's enough to maximize this expression with respect to theta. And now what we're going to do is we'll just take this expression and maximize it with respect to the three parameters, pi, mu, and sigma. And I'll do this quickly because it's just tedious algebra. So here's the ELBO copied over from the previous slide, where our parameters theta are pi, mu, and sigma. So let's first maximize with respect to mu. We take the gradient of this expression with respect to mu and set it to 0. So if you take the gradient with respect to mu, we notice that this does not depend on mu, so it drops out. The logarithm of a Gaussian is just a quadratic form, so we get a minus in front, and then the chain rule gives us sort of sigma inverse times xn minus mu times this responsibility. And if you take a gradient with respect to mu L, where L goes from 1 to k, then only one term in this sum over k contains that mu L, so that sum over k vanishes, and we just have an L left. We set it to 0, and now we can easily rearrange as usual, right? So there's an expression that does not contain x's, it does not contain mu's, so we keep it on one side of the equation. And then there's an expression with a mu, where mu does not depend on n, so we can take it outside of the sum, we rearrange, and we get this expression, which is literally just the weighted empirical mean of the data set, where the weights are given by the responsibilities. Is that okay? Was a bit quick question. Say again? L. So L is just one index that goes from 1 to k. And yeah. Yeah? Pi k, you mean? Yes. So it's still up here. And we want to maximize this expression with respect to it. But we are now currently starting with mu to first get mu optimized. So if you take the derivative of this expression with respect to mu, you see that you don't need pi. Pi is the probability to be in cluster K a priori. So it's just a set of k numbers that sum to 1. Yeah, a priori. Not a posteriori, but a priori. Okay, now we maximize with respect to sigma. So here things get a bit more hairy. You need to do a little bit of matrix differential calculus. There is a rule that says to take the derivative of the inverse square root determinant with respect to the covariance matrix. This is a standard expression you need in Gaussians a lot. Actually, this happens to be this, and the derivative of this expression happens to be this. To show this, you need to write down nasty expressions with sums, expand them in individual terms, and then play around with them. And for this here, you need to use a singular value decomposition and show that it exists, and blah, blah, blah. But you can also read it off from, there are tables of these derivatives that you can find online. if you Google for matrix differential calculus, you'll find lists of all of these properties. And so we can use this here to plug these in, get an expression like this, which looks more ugly, but it's actually just a variant of this expression that we got for the mean. We just get to rearrange, right? So there are terms in here that depend on sigma, and we set this to 0, multiply from the left with sigma, so one of the inverses cancels and the other one stays, and then we rearrange, and we get an expression for the estimate of the covariance that also looks pretty much like what you expect the estimate to look like, right? It's a weighted empirical estimate of the covariance. So it's a weighted sum over the distance to the empirical means. So that's how we set sigma. Now the final step is that we also have to estimate pi. So for that, we take an expression, a derivative of this expression with respect to the mixture weights, pi. And now here's this tricky business where I need to ask you whether you know what a Lagrange multiplier is. Raise your hand if you've heard about Lagrange multipliers before. Okay, that's like 90% of you. And if I asked one of you how it works, you'll probably all put your hands down because you don't know how to use Lagrange. I know. So the story is, I could draw a picture, but I always get it wrong as well if I haven't thought about it before. We want to maximize a function under a constraint. Here we need to make sure that the pi that we estimate actually is a probability distribution. So it has to be a set of numbers that sum to 1. And to do that, we write down the function that we want to optimize plus a function that evaluates to 0 when under the constraint with a multiplier in front called the Lagrange multiplier. And then the game will be to compute the gradient, solve for 0, and find a value for lambda such that this always holds. So we take the derivative of this expression with respect to mu. That gives us this. It's an easy derivative to compute because pi shows up in a very easy fashion up here. Then we solve for this to be equal to 0. We find that pi L has to be set to this, which is actually also an intuitive sort of value because RL, so capital RL, which is the sum along n over RNL, is just the sum of, it is the expected number of data points in each cluster. That sounds like a good estimate for the cluster weights, but it's not a number that sums to 1. So we have to pick a value for lambda that makes these sum to 1, and it's the obvious choice. It's divide by n. Right, so this capital RL is the expected number of data points in each cluster. We divide by the total number of data points. And now we have something that sums to 1. And that's it. That's the entire algorithm. So we'll iterate between, I didn't have a slide for this. Shit. Okay, so I need to show you a slide of, okay, on Thursday I'll show you a slide with the code, the Python code for this, but it's really not that complicated. It's like like k-means, just the changes are we estimate the parameters along using these equations. So we set pi L to something involving the responsibilities. We set the mean and the covariance to something involving the responsibilities and the excess. And then we update the responsibilities not by setting them in a hard fashion like in EM, but by setting them to these numbers, which we can clearly compute when we have mu and sigma and pi. And if we do this, then we get an algorithm that looks like this. On the left, I initialized it at random by picking 2 points from the data set with a standard covariance, standard Gaussian. And then I ran this algorithm for 17 iterations, and now it's converged to this Gaussian mixture model over this data set. So this k-means algorithm, which I used as an entry point into this class of algorithms that have an induced factorization structure, is an algorithm that assigns data to clusters and cluster parameters to the clusters by minimizing an energy function that we can think of as the log marginal likelihood of a Gaussian mixture model. It can be generalized into an algorithm that estimates the parameters of a general log likelihood when you, by introducing latent variables, Z, which create an interesting factorization structure in the distribution. And we can think of this algorithm called EM, expectation maximization, as an iteration between closing a gap between an evidence lower bound and the actual evidence by minimizing KL divergence to the posterior, and then optimizing this surrogate for the evidence lower bound, with respect to theta, and then closing the gap again, optimizing the surrogate, closing the gap again, optimizing the surrogate, and so on. We saw how to use this for Gaussian mixture models to find the maximum likelihood assignment. On Thursday, I'll now give you more historical, we'll move into the 70s and 50s and 60s and 70s, where statisticians and physicists built a big, powerful, but very structured framework around this called variational inference. And then on Tuesday next week, we'll discover that this idea of induced factorization, like we have here in k-means, actually survives to this day in the form of attention mechanisms in deep neural networks. It's just that these days, we don't talk about responsibility anymore. We think about attention. For now, thanks for your attention, and I'll see you on Thursday.